A canonical device. Let us now look at a canonical device, not a real one, and use this device to drive our understanding of some of the machinery required to make device interaction efficient. This has two important components. First is the hardware interface it presents to the rest of the system. Just like a piece of software, hardware must also present some kind of interface that allows the system software to control its operation. Thus, all devices have some specified interface and protocol for typical interaction. So, this will be the start of our study on how the input and output device connect or communicate with our CPU. So the first is the hardware interface presents to the rest of the system. So here the hardware interface, the status, command, and data. So just like a software, hardware must also present some kind of that interface, kind of like an interaction design that the system that allows the system software to control the hardware operation. Thus, all the devices have some specified interface and protocol for typical interaction. So the interface kind of like a protocol for their interaction, kind of like an interaction design, and the TCP/IP protocol, because that's in the next videos we will gonna discuss how TCP or IP becomes the language of the internet, and how in every thing we need some common language or protocol that allow us to speak to each other. So here's an example of canonical device. Later we will discuss a driver interface or software driver that allow us to communicate in detail with the device, and how the operating system abstracted that communication. So the second part, which is these internals of any device, is its internal structure. So the second part of any device, so again we're talking about a hardware device, we're not talking about the software. So first thing a device has is its interface to connect to the software. Another thing is its internals. So this part of the device is implementation specific and is responsible for implementing the abstraction the device presents to the system. So these internals are implementation, meaning they are responsible for implementing the abstraction the device presents to the system. The abstraction provides to the system. Very simple devices will have one or few hardware chips to implement their functionality. More complex devices will include a simple CPU, some general purpose memory, and other device specific chips to get their job done. For example, modern RAID controllers may consist of hundreds of thousands of lines of firmware, like software within a hardware device to implement its functionality. So a more complex, like a RAID controller, will have thousands of lines of firmware, and this is also the reason why a modern operating system that supports a lot of devices has a million line of codes, because of their complex functionality. So more complex devices will include a simple CPU, some general purpose memory, and other specific chips to get their job done or their functionality. So it's kind of like human. You need to have CPU, memory, and disk to be able to do your function. So that's the internal. So here's an example: a CPU, a memory, and other chips that helps to get their function. So the canonical protocol. In the picture above, the simplified device interface is comprised of 3 registers. So these are the registers we're talking about, whether to CPU, to disk, or to memory. So as you can see, they have 3 registers: a status register, which can be read to see current status of the device; a command register to tell the device to perform a certain task; and a data register to pass to the device. Or get data from the device. So by reading and writing these registers, the operating system can control device behavior. So these are register are used to by software to control this device or hardware behavior. So the command are the software way to tell, like, to read it or to write it. What the status shows if can be written or read too. And a data register, so to pass. So this is more like the right part. So this command tells this hardware to perform certain task, while the data to perform that task, let's say we're writing it, are passed into this data interface to pass data to the device or get data from the device. So pass data to and get from. By reading and writing these registers, the operating system can control device behavior. So that's the way operating system control that, by reading and writing each of those register, whether it's status, command, or data interface. So let us now describe a typical interaction that the OS might have with the device in order to get the device to do something on its behalf. So these are the protocol. So this will be the example of a typical interaction of the OS to this hardware. So while status equals to VC, wait until the device is not busy, then write data to data register, write command to command register, whether execute certain functions, variables, etc. Starts the device and execute the command. So that's about starting the it could be a start the device to execute the command. So while status equals to busy, wait until device is done with your request. So it's still the same canonical device. So the protocol has 4 steps. So the first the OS waits until the device is ready to receive a command by repeatedly reading the status register. We call this polling the device. So before the OS can interact with the command or to command that device, it will keep polling first the status to be able to check the status, like while status equals to busy, wait until device is not busy. Second, the OS send some data down to the data register. One can imagine that if this were a disk, for example, that multiple writes would need to take place to transfer a disk block, say 4 kilobytes, to the device. So this sending data are one of the example are sending to disk or data to disk or multiple writes to disk. So let's say it would need to take to transfer this block of say 4 kilobytes to the device. It will take multiple writes or multiple like communication to that data interface. When the main CPU is involved with the data movement, as in this example protocol, so in this example protocol, the main CPU are involved in that. We refer to it as program I/O. So if the main CPU are involved in sending this data. Third, the OS writes a command to the command register. Doing so implicitly lets the device know that both the data is present and that it should begin working on the command. So meaning it send first the data, as you can see, like sending it to the device to be able for that device to execute the command, because without data it won't be able to execute the command. So that's the third. Writes a command to the command register. Doing so implicitly lets the device know that both the data is present and that it should begin working on the command. Finally, the OS waits for the device to finish by again polling it in a loop. So it pulls it in a loop via like continuously checking the status, waiting to see if it's finished. So that's the sequence. First, you poll it and then you write data, and then based on that data, it will execute an output, right? You need that data first to be able to execute something, to be able to output something, right? Because that's the main idea of the input and output device. Finally, the OS waits for the device to finish by again polling it in a loop. Waiting to see if it is finished. It may then get an error code, indicate success or failure. So based on this status will indicate if that command provided or executed to the data is successful or finished. So the first problem you might notice in the protocol is that polling seems inefficient. Specifically, it wastes a great deal of CPU just waiting for the potentially slow device to complete its activity, instead of switching to another ready process and thus better utilizing the CPU. So the crux. So that's the problem. The polling are inefficient. So instead of waiting, the CPU could execute other tasks. Instead of waiting for that slow device to complete its activity. So remember, we're talking about an I/O device here. So instead of having the CPU wait for that input or output, it can process other device or other operation from the operating system. Also remember, we're talking about the I/O here. A simple I/O does not need like CPU or memory, while more complex I/O device need the CPU and memory. So the crux: how to avoid the cost of polling. How can the OS check device status without frequent polling and thus lower the CPU overhead required to manage the device? So the question is that with this simple interfaces, status command data working for us to be able to connect to that I/O device, how can the OS check the device status without that frequent falling and thus lower the CPU overhead required to manage the device? So lowering the CPU overhead with interrupts. So the invention that many engineers came upon years ago to improve this interaction is something we've seen already: the interrupt. So instead of calling the device repeatedly, the OS can issue a request, put the calling process to sleep, and context switch to another task. So you might think that the polling that we use to communicate to the status register are an interrupt. It's not actually an interrupt. The interrupt is what we use to context switch to another process to make better use of our CPU. So without interrupts, the system simply spins, polling the status of the device repeatedly until the I/O is complete. So without this interrupt, the system will simply spin and spin and spin, polling the status of the device or the I/O device until the I/O is complete, indicated by AP. So here is the classic or the inefficient polling. So the disk service the request, and finally process 1 can run again. So the disk will service this polling request, the CPU or the OS request to write something there, or to execute command and change data, and then the disk service the request, and finally process 1 can only run again to the CPU. So that's the inefficient way. So instead, we utilize interrupts and allow for overlap. The OS can do something else while waiting for the disk. So here is the ideal example. In this example, the OS runs process 2 on the CPU, while the disk services process 1 request. When the disk request is finished, an interrupt occurs and the OS wakes up process 1 and runs it again. So an interrupt occurs between those, so that whether it's transferring from process 1 to 2, or from transferring from from process 2 to 1, we're using an interrupt. So thus both the CPU and the disk are properly utilized during the middle stretch of time. And that's a good vocabulary, a middle stretch of time. Note that using interrupts is not always the best solution. For example, imagine a device that performs its task very quickly. Again, note that using interrupts is not always the best solution. For example, imagine a device that performs its task very quickly. The first poll usually finds the device to be done with the task. So kind of like the spin that we have introduced earlier. Not all spin is bad, because if you just wait one and then yield after that, if the process or the thread did not let it go, then it could be time efficient. So what better is depending on your workload, really, because sometimes like configuring it, and most operating system allows the configuration on what number or how many number of polling are you actually willing to wait before you yield that to the other threads. So again, for example, imagine a device that performs its task very quickly. The first poll usually finds the device to be done with the task. Using an interrupt in this case will actually slow down the system. Switching to another process handling the interrupt and switching back to the issuing process is expensive. If the speed of the device is not known or sometimes fast and sometimes slow, it may be best to use a hybrid that pause for a little while and then, if the device is not yet finished, uses interrupts. So again, if the speed of the device is not known or sometimes fast and sometimes slow, it may be best to use a hybrid. That pause for a little while and then, if the device is not yet finished, uses interrupts. So that's the hybrid that what we discussed, like polling for a little while and only for a certain time or certain sequence or certain frequency that it will do the interrupt. So this two-phase approach may achieve the best of both worlds. This is also what we've done in two-phase locks in the previous video. The combination of waiting, the spin, and also the cue to achieve fairness for locking thread. So as you have noticed, those types of solving problem is very there's a recurring pattern why those adopting pros and cons for different type of solution are used in operating system. Another reason not to use interrupts arises in networks when a huge stream of incoming packets each generate an interrupt. So when a huge stream of incoming packets from your requesting to your operating system to be able to execute your device, it is possible for the OS to leave lock, that is, find itself only processing interrupts and never allowing a user level process to run and actually service the request. So because of that, it will only process interrupts because it was overwhelmed by a huge packet that is requesting to write or read something on your I/O device. So for example, imagine a web server that experienced a load burst because it became the top rank entry on Hacker News. In this case, for that web server, the operating system, it is better to occasionally use polling to better control what is happening in the system or whether it will all proceed with the interrupt. So it may be best to use that polling in this type of web server. Because again, a web server has an operating system too that deals with its I/O. So in this case, it's better to occasionally use polling to better control what is happening in the system and allow the web server to service some request before going back to the device to check for more packet arrivals. So again, in this case, it is better to occasionally use polling to better control what is happening in the system and allow the web server to service some request before going back to the device to check for more packet arrivals. So instead of like interrupting the I/O, it will poll first before serving the other interrupt for it to be able to service a normal user level program. So again, it depends on your workload and your situation. So while waiting, other requests may soon complete, and thus multiple interrupts can be coalesced into a single interrupt delivery, thus lowering the overhead of interrupt processing. So while waiting or polling for that status register, other requests of the user may soon complete, and also it will coalesce those multiple interrupts into a single interrupt delivery, and thus lowering the overhead of interrupt processing, because you don't need to do much context switch that eventually will turn into context switch and context switch, and then which will make the OS do that livestock. Of course, waiting too long will increase the latency of a request, but waiting, calling will increase the latency of the request for an actually legitimate I/O from network packet. So, a common trade-off in systems. So you need to be able to distinguish that. So more efficient data movement with DMA. The crux: how to lower PIO overheads. With PIO, the CPU spend too much time moving data to and from devices by hand. How can we offload this work and thus allow the CPU to be more effectively utilized? So because of that, if the CPU are involved in transferring data to and from the disk, we call that PIO, right? So let me just go back there. So when the main CPU involved with the data movement, as in the example protocol, we refer that to the PIO. So that's one of the efficiency that we will gonna introduce, because instead of more complex I/O device that requires CPU for this transfer, how about we introduce another device, which is the DMA? So unfortunately, there is another aspect of our canonical protocol that requires our attention, in particular when using program I/O to transfer large chunk of data to that I/O device. So the CPU is once again overburdened with a rather trivial task, and thus waste a lot of time and effort that could be better spent running other processes. This timeline illustrates the problem. So here, 11111 CCC. So what is C? So in the timeline process 1 is running and then wishes to write some data to the disk. So this writing, takes a lot of time because it's transferring data. So again, when a CPU is involved with this, you can't use the CPU for other processes. Hence the creation of a DMA. So it then initiates the I/O, which must copy the data from memory to the device explicitly, one word at a time. So this is what happening when you're copying or saving from memory, like in your live memory to your disk. You're doing this CCC, and then before actually trying to writing it inside or doing something inside it, like the command and data register underneath. So when a copy is complete, the I/O begins on the disk and the CPU can finally be used for something else. So after the copy, so it need to copy. The reason why we have this CCC is because the transferring needs to be specified from memory to device one word at a time. So mark C. So yeah, whenever you're copying to the disk, you're copying words. You're not copying program or code. You're copying code, words. Again, in the end, this program are boiled down to strings and numbers, right? So that's words. And actually, the number could be a string as well, right? So, I mean, a word can be a combination of string and word. So when the copy is complete, the I/O begins on the disk, and the CPU can finally be used for something else. So how about this? So a DMA engine, like this, is essentially a very specific device within a system that can orchestrate transfers between devices and main memory without much CPU intervention. So again, a DMA engine is essentially a very specific device within a system that can orchestrate transfers between devices and main memory. So from memory to the I/O without much CPU intervention. Again, without much, because CPU is still involved, but it's only a little bit, and it can only be used. It can now be used for other threads. So to transfer data to the device, for example, the OS would program the DMA engine. So to transfer that data, from memory or from the CPU, or from the CPU memory or memory to the disk, the OS would program the DMA engine by telling it where the data lives in memory. So this DMA are programmed to be to know where that data that you're trying to copy or write to the disk lives in memory, how much data to copy, from what virtual address space is that, and which device to send it to, and which the I/O disk. So at that point, the OS is done with the transfer and can proceed with that other work. So after it program it, like, telling the DMA you do this, they can now execute it, because this specialized device, since they're specialized, can do better copying, and then the OS can move to other threads. So here, when the DMA is complete, the DMA controller raises an interrupt. So when the DMA is complete, the DMA controller raises an interrupt. So the one raises an interrupt now is not the disk and the CPU, it's the DMA controller for the OS to take over and then run the so here, when the DMA is complete, the DMA controller raises an interrupt, and the OS thus knows the transfer is complete. So here's the revised diagram. So the OS will now transfer the actual writing of data instead of that. The now, since the data, we need the data before we can execute a command. Now the OS know when that to communicate now with the I/O device to now execute the command. So that's how, and then run the process 2. So once the disk complete with its stat, that's how we poll now. So after we poll that, in the end, check the status if the I/O is complete. It will now go back to that first process. So from the timeline, you can see that the copying of data is now handled by the DMA controller. So methods of device interaction. So the crux, how to communicate with devices. How should the hardware communicate with the device? Should there be explicit instructions, or are there other ways to do it? Over time, two primary methods of device communication have developed. So again, how to communicate with devices. How should the hardware communicate with the device? Should there be explicit instructions, or are there other ways to do it? So again, how should the hardware communicate with the device? Should there be explicit instructions, or are there other ways to do it? Over time, two primary methods of device communication have developed. The first, oldest method, used by IBM mainframes for many years, is to have explicit I/O instructions. So again, let me repeat. So how would the CPU and memory communicate with the disk I/O or any I/O device? Should there be explicit instructions? So the answer is that IBM, the first oldest method used by IBM mainframes for many years, is to have explicit I/O instructions. So these instructions specify a way for the OS to send data to specific device registers. So this is now the data, because earlier we have a canonical example where we have status, command, and data. Now here, IBM provide an explicit I/O instruction. They specify a way for the OS to send data to a specific device register. So this is how you send data on that IBM mainframe. So for example, on x86, the in and out instruction can be used to communicate with devices. So the in and out instruction are used to communicate, to send data on that data interface. For example, to send data to a device, the caller specifies a register with the data in it. So to be able to write data to a device, the way to do that on this first, x86 in and out, is to specify the register. What's the register are you trying to write data in? And specify port which names the device. So which device are you trying to send to? So that's how the explicit instruction works. So executing the instruction leads to the desired behavior. Such instruction are usually privileged. So this is how, when we drop to the OS, what's happening behind the scenes. So this instruction is the executing the instruction leads to the desired behavior. So such instruction are usually privileged. The OS control devices, and the OS thus is the only entity allowed to directly communicate with them. The second method to interact with devices is known as memory map I/O. So the other methods which we asked earlier, aside from explicit instruction, are memory map I/O. So with this approach, the hardware makes device registers available as if they were memory location. So the CPU makes that register available as if they were memory location. So to access a particular register, the OS issues a load to read or store to write the address. The hardware then routes the load or store to the device instead of main memory. So the CPU will route that load or store or read or write to the device instead of main memory. So that's the reason why it's memory map I/O, because the transfer of data and the instruction like to communicate to that data interface and then eventually command by the OS is actually not routed to memory. Instead, to the device itself. So the device registers small special memory inside the device controller. So these device register, are implemented using a small memory. That's why you don't need to go through the memory or the main memory of the system. There's a small memory within this device. Inside the device controller are mapped into the CPUs inside the device controller. Are mapped into the CPU's physical address. So again, the device registers, which is a small special memory inside the device controller. So inside that device controller, are mapped into the CPU's physical address space. So the reason why is because it is mapped. So this small, memory are actually programmed to be mapped. That's it. That's the reason it's memory map IO. It's programmed to be mapped just beside the CPU physical address. That's why it's able to communicate this small memory instead of the main memory. So the data or command being sent by the CPU does not actually go through main memory in that step, because that again the read or write are directed. That's why it's memory map in that small memory. So the device registers again is a special small special memory inside the device controller that handles the data or command interface we discussed in canonical device. It does not actually go through the main memory in that step. The CPU accesses the device registers directly. It accesses the device registers directly by passing RAM, even though it uses a normal memory instruction. So it bypasses RAM though it uses a same or normal memory instruction, because it's still a memory. It's just a small memory used to be directly communicate to provide command and data interface. So however, sometimes main memory is still involved later when the device transfer large chunk of data like disk read or network packets. The DMA, direct memory access controller, lets the device write or read directly to from main memory without CPU involvement. So the difference is that this direct memory access controller lets the device write or read directly to from main memory without CPU involvement, but the initial control or command like start read or check status happens through the memory map registers, not RAM. So that it directly access small memory, that RAM. So the exception is that when the device transfer large chunks of data like the disk reads, saving like downloading from the OS or from the web to directly to your disk. So that's the it still access the DMA, which is the direct memory access controller, lets the device write or read directly to from main memory. So the DMA directly read or write from main memory and then copy it to disk without CPU involvement, because the CPU would be used to other processors. So the CPU uses normal load or store instructions that look like memory access. So again, the CPU uses load or store instructions. The CPU uses normal load or store instructions that look like memory access. So again, the CPU uses a normal load or store instructions that look like a memory access, but it's actually uh, access to that special memory. So again, it's read and write because it's an I/O device, right? Anything that's not I/O device are discussed in the previous video. I/O operation is discussed in the previous video, which in that case, like you're using other operations, right? But the hardware reroutes them to the device. Memory map I/O doesn't touch RAM at that control step. So there's not some great advantage to one approach or the other. You know, the memory map approach is nice in that no new instructions are needed to support it, but both approach are still in use today. So fitting into the OS, the device driver. So this is what I'm saying. How the modern OS actually abstract a lot of details on communicating with the devices, and that's the reason also why people say that it's a lot of code when in reality it's mostly device drivers. So one final problem we will discuss: how to fit devices, each of which we have very specific interfaces into the OS. So how do you fit that into the OS? Like, you have that interface, the command, the data. So how do you fit that now into the OS? We would like to keep into the OS, which we would like to keep as general as possible. For example, consider a file system. We'd like to build a file system that work on top of SCI disk, IDE disk, USB key change, and and so forth. So how do we build a file system, from the OS that like support these multiple drive or disk or devices? So the answer, of course, is abstraction, or like this device driver that handle the details, and we would like the file system to be relatively obvious to all of the details of how to issue a read or write request to these different types of drives. So how to build a new device neutral OS. So how can we keep most of the OS device neutral, thus hiding the details of the device interactions from major OS subsystems? So again, how can we keep most of the OS device neutral, thus hiding the details of the device interactions from major OS subsystems? So how can we because the OS subsystems already has a complex interactions, right? The virtual machine, the threads, the CPU scheduler. How can we now hide the details of this device interaction to support as many as possible from this um, device interface, or device driver? The problem is solved through the old age technique of abstraction. At the lowest level, a piece of software in the OS must know in detail how a device works. We call this piece of software a device driver. And any specific of device interaction are encapsulated within. So here's the application, the user one, POSIX API that provides open, read, write, close, etc. to our the file system that manage that, and raw. So these are the generic block interface to then be communicated by application, and this generic block interface are actually now communicating with a specific block interface. But again, as you notice, they are in kernel mode, which is the device driver, SESI. So the device driver is at the bottom, as you can see, just below the specific block interface or protocol specific reader, right? So as you can see in the diagram, a file system and certainly an application above is completely oblivious to the specific of which this class is it is using. Simply issues block. So that application and file system does not actually know which specific this class it's using. It simply issues block read and write request to generic block layer, which routes them to the appropriate device driver, which route them to this specific device driver, which handle the details of issuing specific requests. So this device driver are the the specific device driver or specific interface are responsible for the specific request. Although simplified, the diagram shows how such detail can be hidden from most of the OS. So here, it was hidden like that, like application, POSIX API, general block, and then specific block interface, which is the device driver. So the diagram also show a raw interface to devices, which enables special applications such as file system checker, described later, or a disk defragmentation. So whenever you're defragmenting your disk to be able to read it, this is where it is. To directly read and write blocks without using the file abstraction, which is this POSIX API, file system, generic, and then specific. Most system provides this type of interface to support these low-level storage management applications. So again, most systems provide this type of interface to support these low-level storage management applications. So most of the operating system actually provides this, like the raw part, to directly read and write blocks without using this file abstraction, because it supports this low-level storage management application like defragmentation. So note that encapsulation seen above have its downside as well. If there is a device that has many special capabilities but has to present a generic interface to the rest of the kernel, those special capabilities will go unused. So there is a downside on this, because if you abstract it and make it general to present to the kernel, those special hardware interface such as we develop in the threads library, different locks such as the fetch and add, the load and store, etc., or will go unused, which are very rich. So like this situation arises, for example, in Linux with SCSI devices, which have very rich error reporting, because other block devices like ATA or IDE have much simpler error handling. All that higher levels of software ever receive is a generic EIO or generic IO error code. Any extra details that SESI may have provided is thus lost to the file system. Interestingly, because device drivers are needed for any device, you might plug into your system. Over time, they have come to represent a huge percentage of kernel code. Studies of the Linux kernel reveals that 70% of OS code is found in device drivers. For Windows-based systems, it's likely quite high as well. Of course, any given installation, for any given installation, most of the code may not be active. Only a few devices are connected to the system at a time. As drivers are often written by amateurs instead of full-time kernel developers, they tend to have many more bugs and thus are primary contributor to kernel crashes. So for any given installation, most of that code may not be active. For example, like the OS, simple, you just need a simple OS for a user. Those device driver code that will support like higher level device as well would not be active. Therefore, you need a further installation because it really depends on your workload, right? Additionally, more depressingly is that as drivers are often written by amateurs, not experts, they tend to have many more bugs and thus are primary contributor to kernel crashes. So that's the reason why the operating system crashes, because of those code. So that's a usual issue. Case study. So a simple disk IDE driver. So to dig a little deeper here, let's take a quick look at an actual device, an IDE disk drive. We summarize the protocol as described in this first reference. We'll also pick. So we're gonna summarize the protocol as described in this here. We'll also pick at the x86 source code for a simple example of working IDE driver. Again, we'll also peek at the x86 source code for a simple example of our working IDE driver. IDE stands for Integrated Drive Electronics, also known as ATA, Advanced Technology Attachment. It's an old but foundational disk interface standard that defines how CPU communicates with hard drives. So here are how we communicate to that ATA we described earlier. Here, ATA. So what is the actual device or specific device driver code for that? So that's an example, the IDE interface. So it is provided by ATA to the generic block interface by the OS. So here is the XV6 IDE disk driver, which is simplified. So how do you make use of this IDE interface? So again, this driver needs to provide some interface for its basic commands such as status, command, and data. So command, these are the interface for that that it provided. So these are the code. Now these are the actual driver. An IDE disk presents a simple interface to the system consisting of 4 types of register: control, command block, status, and error. So control, as you might notice, there's no data now. We only kept the command and the status interface or register. These registers are available by reading or writing to a specific I/O address. So that kind of like how the DMA locate the address of memory and how it copies it before it interrupts the disk. These registers are available by reading or writing to specific I/O address, such as 0x34 3F below, using on x86 the in and out I/O instructions. So these are the, again, how you communicate to it via reading or writing. So these are more like encompasses the DMA as well as the data transfer that have talked in canonical device. So here 0x34, the basic protocol to interact with the device is as follows. So here's the basic protocol. Wait for drive to be ready. So read status, register 0x17 until drive is ready and not BC. So these are the code for that. So again, it still has the BC to communicate, but it's more specific. So write parameters to command registers. Again, for like writing, right, you need to know the register and then the device number in DMA, as well as the data. You need to be able to have that data, because again, we need to execute the data first, or to transfer data before we can execute the command. So here, these registers are available by writing or writing to specific IO address such as 0x3 F6 below using an on x86 the in and out IO instructions. The basic protocol to interact with the device is as follows. Assuming it has already been initialized, so um, assuming that the device has been started already, again, just like with a DMA, you need to start it first. The basic protocol to interface with that is this. So write parameters to command registers, write the sector count, logical block address of the sectors to be accessed, and drive number like master 0x00 or slave 0x10, or IDE permits just to drive to command registers like 0x1f2 to 0x1f6. So that's finding the block. After you find the register, or after you read the status register to wait to see if it's ready or busy, you now write the sector count, the logical block address, and the drive number, right? Start the IO. Write the read or write command to command register 0x1f7. So these are the example. ID static int IDE underscore wait ready. So it's still like an int, static void IDE underscore start underscore request, etc. Right? It's still int, like a hardware initialization code we described before. So data transfer for writes, wait until the drive status is ready, and DRQ drive request for data. Write data to data report. So again, data transfer for writes, wait until drive status is ready, and DRQ drive request for data. Write data to data report. So here you need to wait for the drive, of course, status to be ready, and DRQ drive request for data and write data to report. So you also have to drive, request for data to the drive to read it, or write data to the data port. Handle interrupts. In the simplest case, handle an interrupt for each sector transferred. So for each sector, you need to be able to handle interrupt. More complex approaches allow batching and thus one final interrupt when the entire transfer is complete. Error handling. After each operations, read the status register. If the error bit is on, read the error register for details. So these are the error handling. After each operation, read the status register, or the status of that register. If there's an error, that's actually how you check the error in device driver. So here, void IDE underscore W struct buff asterisk buff B. So acquire IDE lock. So as you can see here, you walk the queue, add request to end. If queue is empty, send request to end. So these are the whole code basically. So So here, the XV6 IDE disk driver simplified. So most of this protocol is found in the XV6 IDE driver. So that allowed protocol or language or interface for the OS, which after initialization worked through four primary functions. So these are actually the four primary functions of that IDE code driver. The first is IDE underscore W, which queues a request if there are other pendings or issues it directly to the disk. So it will queue the request or walk you, and then it will wait for completion if there's other pending or issues it directly to the disk via start underscore request. So here void. As you can see, we still use the void here, the C code void. So in either case, the routine waits for the request to complete and the calling process is put to sleep. So this is how you put the sleep. That's the reason why the other processes are being put to sleep when you're writing, is because of this code, the device driver. This is how it does this. So this is the IDE underscore start underscore request function, which directly read to disk if there's no other waiting. The second is IDE underscore start underscore request. So we here IDE underscore start underscore, which is used to send a request and perhaps data. In the case of a write to the disk, the in and out x86 instructions are called to read and write device registers respectively. So again, the second is IDE underscore request, which is used to send a request and perhaps data. In the case of a write to the disk, the in and out x86 instructions are called to read and write device registers respectively. So here how you send the request. If you spend empty, send request to disk. So IDE start and then wait for its completion, and then void IDE underscore int. So the start request routines uses the third function, IDE underscore wait underscore ready. So here, so generate an interrupt. So how many sector 8 LBA before issuing a request to it. So finally, the INTR, which is this, void IDE is invoked when an interrupt takes place. It reads data from the device if the request is read, not a write. It wakes the process waiting for the IO to complete. So here, waiting process. If it's if the request is read or write, so it uses an if else statement as well. And if there are more requests in the IO queue, so start next the request, not just the next IO, via the start request. So here IDE start request if one exists. So the start request, which is this IDE underscore start, use actually the IDE underscore wait underscore ready to ensure drive is ready before issuing a request to it. So that's how we check if the drive is ready to be written to. That's the code for that. Now historical notes. This we were gonna discuss where this all idea came from. Interrupts are an ancient idea existing on the earliest of machines. For example, the Univac in the early 1950s had some form of interrupt vectoring, although it is unclear in exactly which year this feature was available. Sadly, even its infancy, we're beginning to lose the origin of computing history, because the computing industry, or computing is its in infancy on its industry. We're losing the history, where it came from. There's also some debate as to which machine first introduced the idea of DMA. For example, Krut and others point to DYSEAC, a mobile machine which at the time meant it could be hauled in a trailer, whereas other thinks the IBM Sage may have been the first. Either way, by the mid-50s, systems with I/O devices that communicate directly with memory, such as this DMA, and interrupted the CPU when finished, existed. So this DMA existed for other machines in 1950s. The history here is difficult to trace because the inventions are tied to real and sometimes obscure machines. For example, something that Lincoln loves, the X2 machine was first with vector interrupts, but this is hardly clear. What is certainly clear, as people built these early machines, it became obvious that I/O support was needed. Interrupts, DMA, and related ideas are all directed outcomes of nature of fast CPUs and slow devices. If you were there at the time, you might have had similar ideas. So you should now have a very basic understanding of how an OS interacts with the device. Two techniques, the interrupts and DMA, have been introduced to help with device efficiency, and two approaches to accessing device registers, explicit I/O instructions, and memory map I/O have been described. Finally, the notion of device driver has been presented, showing how the OS itself can encapsulate low-level details and thus make it easier to build the rest of the OS in a device-neutral fashion.